All right, how's it going? Tired? Were you up all night programming or something?
Until to 7:58.
Really?
Yeah.
Awesome.
Cool.
Get things done?
No.
You get close?
Yeah, we're close.
Okay, cool. So PA4 is tricky, right? And if you didn't get it finished, if your delete function doesn't work, if your breadth first traversal doesn't work, right, don't panic. This is not unusual. It's a complex assignment. There's lots of pieces to it. Deletion is tricky because there's edge cases, and it's kind of tricky to debug. If it works, great. If it doesn't work, it's not always clear how to sort of figure out what's going on. And you've got, your algorithm in your head. You've got pictures of trees that you're trying to update on paper. You've got your code, which is what you're asking the computer to do, and you've got GDB running, which is telling you what the computer actually is doing. And you're trying to sort of harmonize all of those different pieces together and figure out where the one small mistake, where you have a right instead of left, or you have an equal instead of an equal, or something like that. And it's challenging, right? The benefit to doing this is actually getting better at doing this kind of thing, getting better at GDB, getting better at working through code or putting in print statements or drawing pictures of trees. That's the real reason for these exercises, right? Not to have 65 copies of a delete function so that I can go out and sell them on eBay or something. And if you get it to work, that's great. It's a really cool feeling when everything's like just right? But even if you're not at that point, right, there's still a lot of value that you most likely got out of doing this. So it's all beneficial. So delete is probably the hardest thing to get nailed down just right. And breadth first traversal is probably the second one. And breadth first, right, the algorithm is simple. It's 4 steps. But the pieces involved in that, right, you have to modify your queue so that it's a queue of pointers to tree nodes. And if you miss one spot somewhere in your code where you still have an integer, right, all kinds of crazy things can go wrong. You've got to be able to tell when your queue is empty, and if you're off by 1, all kinds of crazy things can go on. So sometimes you don't print all your nodes, sometimes you print a null node at the end, sometimes it always segfaults because it's trying to print something with a null. And C in particular is really easy to get in trouble with, because C is kind of like a high-level version of assembly language. It'll do what you ask it to do. If you say if parentheses x equals 0, it'll say, oh, you must want to set x equal to 0, and it'll do it for you. Java, Python, other more modern languages really work to sort of keep you out of those kinds of troubles. As you're typing, it'll turn bright red and say, you made a mistake, and I can fix it for you. Click here and I'll fix it, And that's great when you're actually doing, something in a production environment, but it kind of hobbles your learning of what's going on because it's doing all that for you. So when we get into 223, it'll be a very different feeling. It's kind of like, driving a Cadillac versus a bicycle that keeps breaking down. But this is why you'll be able to do things like work in a Java environment or a Python environment or C# or whatever, because you're understanding the stuff that's going on lower level. So we'll look at some code on Monday for PA4. So I've opened up some quizzes, the remaining quizzes. So quiz 5, 6, and 7, and these are due on the 8th, so a week from today at, I think it's due at midnight. But do these soon. Do these like over the weekend or something. It's 5 questions each. So one of these is on trees, one of them is on heaps, and one of them is on tries. Okay, and it's 5 multiple choice questions, so they should be pretty straightforward to do. But don't leave them for like Thursday night and then say, can't find the quizzes, or something like that. So those 3 quizzes, 5 through 7, are open now. All right, so let's talk PA5, and then let's talk more knapsack problem, and then we'll go in and look at the details of PA5. Yes?
I just have a minor question before.
Sure.
In our SLP report,
Mhm.
it mentions competitive analysis.
Yeah.
Do we have to compare it to something similar to what our project is demonstrating?
You know, let's look at this, because these are always like subject to interpretation. And it would be nice if we all interpreted them the same way. So let's actually take a look at this.
The other minor question I had is a solution block diagram, which was listed under solution specifications.
Okay. So yeah, you're filling in this template to upload. And looks like this is due, what's the 4th? Monday?
Yeah.
Okay. So first thing, actually put in the name of your project and the date, and then your team name and the team members. Don't just leave it as project title, comma, date, because that looks kind of unprofessional. So fill in the top information. Okay, so problem definition. What is it that you're trying to do? I'm trying to create a game. I'm trying to create a mousetrap. I'm trying to create something that erases the whiteboard by pressing a button. So statement is just a description of your problem. Scope is basically what are the bounds on my project, right? Am I going to make a mousetrap that works on every type of mouse in every type of situation, or is this only going to work on a mouse that's trapped in a room with no way out, or whatever, right? Schedule is just sort of, you know, here's where I'm at, this is where I plan to be at the end of June, a few milestones, and then resources is very high level view of what do I need for this. Okay, this is going to take, you know, $50, and I need to get a laptop or whatever. So competitive analysis. If this is not a totally novel idea that's never been thought of before, and usually it's not completely novel, pretty much anything that we think of doing, somebody else has thought of, often like 100 years earlier. So, so assuming it's not completely novel, other people have done similar things. What are the main approaches that somebody else has taken? Right? I want to make a first-person shooter video game. Okay, it's not the first one that's ever been created. There's a ton of them out there. So just pick a couple of competing solutions that are, I don't know, representative of what's out there, and compare and contrast your approach. And it doesn't have to be novel, right? If you're making a first-person shooter, probably a big stretch to think I'm going to come up with a concept in a first-person shooter that's never been thought of before. Okay, and you're competing against, you know, multi-billion-dollar companies. So we're not looking for, you know, something that will convince an investor to give you $1 million. But that's kind of the mindset. So just sort of play with it a little. You know, other people's systems are expensive, and mine's going to be free. Or you know, mine, you're going to be able to change the code to customize it in some way. So just sort of give the reader some idea of like some other solutions that are in the same or similar problem space, and just kind of compare and contrast. Does that make sense? Potential applications is kind of self-explanatory, but you can be a little bit creative, a little bit salesy here. So if you're making a game, what are the applications? Well, this can help students during exam week when they've been studying too long and they need a break, right? And they can spend some time on this game, and it will help them do better in school.
So what if there are like components of an application you're making that could have potential applications outside of just what you're working on?
Sure, yeah, you can definitely talk about that. So you can kind of think of, you know, going to a venture fair where people have millions of dollars to give to people with good ideas, and this is your elevator pitch. This is your one-page presentation of why they should give you some of their money. So you can do a little bit of marketing in here. And then solution specifications. So block diagram. Well, if you're making a piece of software, block diagram may not be entirely appropriate, but maybe a flow chart. Or if you're writing a program that, you know, is modularized into 4 pieces and there's some interesting relationship between them, you could do that. But you don't have to have a block diagram unless it makes sense. So I think Izad put this together and might have been thinking more about electrical engineering students, where you have, you know, here's an input sensor and here's a processor and here's a power supply and here's some output device. But even with software solutions, block diagram might make some sense. Operational description, component specifications, kind of self-explanatory. And you can also, you know, if you go down the hallway, past the collaboratorium, keep going down the hallway, the whole left wall is filled up with posters from past SLPs. And you can get some ideas from browsing those what some of these things might be.
So if I'm taking a Zod's engineering class and
Yes.
I have one of these, do I just turn mine in?
Yeah, so if you're computer engineering, you're already doing these for another class, for Izad's class, go ahead and just send me a copy of it, right, upload it as normal. But if you can put a comment on there saying you've also uploaded this to Izad, it'll save us from printing 2 copies. And then you'll present at the fair for his class and you get credit for this one as well. And the extra credit sheet, you can either just show it to me and I can sign off on it then, and you can give it to Izad, or you can make a copy or whatever. But no, you don't have to do 2 projects or 2 posters or anything. So does that help with solution specification?
I would say it did, but I don't think I heard all of it.
Basically, don't worry about a block diagram unless it makes sense.
Okay.
If what you're doing can be described in terms of a block diagram or a system diagram, go ahead and use that. If it's better with a flow chart or you know, a short set of pseudocode, whatever makes sense. Basically, you're trying to present your solution, but you've only got half a page to do it in. So whatever's going to make the best presentation. And I grade you primarily on turning this in on time, right? And turning it in on time gets you a printout of it in hard copy form for the presentation. But I don't, particularly in winter quarter, I don't really like go down and critique like individual words. Like, well, this isn't a block diagram, -10, right? So I'm really looking for, you know, what's your problem that you're working on? Not what's your problem. What's the problem that you're working on? What's your proposed solution? Details like that. And you can bounce a draft off me if you want, and I can give you feedback on it.
How will we do a competitive analysis if the closest technical product is, closest comparison is Wii remote or Wii system?
Well, so assuming that you're not going to come up with something that's like, you know, hugely better than the Wii.
It's not.
Okay.
It's a downgrade.
It's a downgrade, but
It's a wired connection.
Okay, it's a wired connection, so it's more reliable, right? Just the fact that you know, it's a learning platform, right? You're doing this because you're trying to learn how to do something related to
Computer gaming.
Yeah. And you can't really do that with a Wii because it's kind of a closed platform. So,
Okay.
yeah.
That makes sense.
In the end, after June, these projects usually get uploaded to a website, and your final report includes your licensing terms. And if you want this to be totally open source, we'll make everything available to the world. If it's something that you actually might want to commercialize or you want to keep it proprietary, you can put that in your final report and say, this is proprietary, don't publish it anywhere, I'm giving this to you just so you can give me a grade, right? And then we'll keep it proprietary. But most often students submit this stuff, they just leave it totally open source, and then it's basically a resource other people can use to learn from. And that's a huge potential advantage over a commercial equivalent that is kind of a closed box.
If we do come up with $1 million idea,
Yeah.
would Clark College own it?
Nope. Yeah, so you can put down, I'm not a lawyer, but as far as I understand, right, doing this as an SLP does not mean that Clark has any interest in it. But you definitely, in your final report, you want to say, this is proprietary, don't put the code, schematics, etc. up on the website, and we'll treat it as your intellectual property. But you got to sign your poster for me so I can sell it later and get rich. All right, so should we talk about PA5? All right, so let me talk about high-level details first. So PA5 is due on Monday, March 11th. It's not 2 weeks from today, because 2 weeks from today is the last day of the quarter. So this project is due in about 11 days, 10 days. It's a week from Monday, so don't be startled by that. And tell your friends who aren't here, if you like them, that it's due on Monday. It's a group assignment. Okay, so you can work in up to groups of 4 people. And the reason that we do group assignments in here is because more often than not, when you're in industry, chances are you're going to be working on a team. Unless you're at a very small startup or working for yourself, for example, chances are you're going to be working on a piece of a project, and there may be 10, 20 other programmers working on other pieces, and there may be a team of people working on integrating those pieces together, and there may be another team that's working on testing the integrated product, and another team that's working on documenting it, and a marketing team, and all these different players, right? And you're one piece of that. And so we want you to have some experience with, in this case, doing the coding part in a group. So this means figuring out how you're going to take this assignment and break it into pieces. And I'd like you to spend some time doing that up front. So sometimes I've had people and everybody went off and they all wrote their code, and then whichever one seemed to work best, that's what the group turned in. Okay, that works, but it's really kind of losing the benefit, the bigger benefits of working on a team. So there's a lot of pieces to PA5, and I'd like you to spend some time up front working as a group to understand the problem, and then make some deliberate decisions about, okay, here's how we're going to partition the work. And part of what I want to see in your presentation of this is a discussion of the group aspect of the project. So beginning on that Monday the 11th, each group's going to come up and present their PA5 to the class. And you'll show us the project, you'll show us how it works, you'll talk us through the codes, interesting pieces, but I also want you to talk about the group aspects. So this was the people in the group, this was how we decided to split it up. After a week, we discovered that this piece that this person was doing was way too big, so we all started working on that, etc., etc. All right, so let me give you some more details on the knapsack problem, and then we'll look at details of the programming assignment, which is the knapsack problem. So knapsack problem begins with the idea of an inventory. So remember, you've got a bag with some capacity, and you're trying to put stuff in this bag in order to maximize the value of stuff. So here's what your inventory might look like. It's going to have a weight, it's going to have a value, and it's going to have a name. So our 1 pound item is worth $10, and that's a mouse. And we have a 2 pound item, which is worth $21, and that's a hard drive. And we have a 5 pound item, which is worth $56, and that's a book. And we have a 7 pound item, which is $78, and that's a headphone. Those are heavy headphones. And I'm just going to think of this as item 0, item 1, item 2, item 3. All right, we got capacity of 10 pounds in our bag. What should we put into our bag in order to maximize the value? What do you think?
As many of the most expensive stuff first, and until you hit the maximum.
Okay, so if we start with the most expensive stuff, that's the headphones.
What I would do is I would take the value and divide it by the weight.
Okay, take the value and divide it by the weight. Okay, so let's try most expensive first. That would be 78. Would be 7 pounds, and then throw in the hard drive is 2 pounds, and then throw in the mouse, which is 1 pound. So that's $109. So your idea is find value over weight. So a mouse is worth $10 a pound, a hard drive is worth $10.5 a pound, a book is worth $11.2 a pound, and headphones are worth 11.142857. There's a reason I know that, per pound. So if we look at the most valuable item by weight, that's a book. And if we have 2 books, that's $112. So that's a better solution. And logically, there's no way we're going to do better than that. Because that's the greedy solution, right? Take the most valuable item, fill up our bag with as much of that as we can, and if we take 2 of those, it fills our bag exactly. There's nothing left over. And so it's kind of like the fractional problem where we take fractional amounts of things. The greedy solution always works there. But if we don't luck out, and if our capacity was, say, 9, the greedy solution will fail you. Because the greedy solution would say, let's take 1 book, which is worth 56. That's going to weigh 5 pounds, so we got 4 pounds left. The next most valuable item is the hard drive, so let's take 2 drives. And that's worth $21 each, so that's going to get us $42. So that's $98. But we can actually do
A
better.
headphone and a drive.
Yeah, so if you do 1 headphone, that's worth $78. Uses up 7 pounds, leaves us with 2 pounds. Take 1 drive. That's worth $21. That gets us to $99. So this is the whole trick to the knapsack problem, is that because we can only take integral amounts of things, a greedy algorithm doesn't always work. So we got to find a different way to solve this.
Find all the values that could be placed in the box and compare them to find the.
Yes. So if we can find all the possible values and compare them, we'll definitely get the best solution. But we got to be careful how we do that, because if we just go about taking all possible combinations, it's going to explode. We're going to have so many combinations, this is not going to be practical. For 4 items, it's not too bad. Well, if our capacity was 1,000, though, we could have 1,000 mice, 500 drives, 200 books, and 140. Yeah. Well, we're basically going to do that, but we're going to use a very particular approach. So I'm going to imagine that I have an array of weights and an array of values. So this is our inventory. And we can also have an array of names, but that's not going to come into the calculation. That's just for making things look nice later. So we have this array of items starting from item 0 that tells us the weight and the value of each item. And our whole goal is to create a function which I'm going to call maximum value, MaxVal. MaxVal, you give it a capacity and it returns the maximum value that you can get by putting things into a bag with that capacity. And we're going to talk about MaxVal for the next 20 minutes, so make sure you know what this function is doing. It takes a capacity and it returns the maximum value we can get from a bag that holds that much. So if this is my inventory, this is what's in the arrays, and I call my function MaxVal9, it should give me back 99. If I call MaxVal10, it should give me back 112. And this is the function we're going to write. So fix in your mind MaxVal is a function that takes a capacity, gives me the maximum value. Well, here's how we're going to come up with the value of MaxVal. We've got, in this case, 4 items. I'll pick on 4, but obviously you want to generalize this to however many items you have. But suppose we've got 4 items, items 0, 1, 2, and 3. There's some unknown combination of those items that if we put those into our bag, we get the maximum value. Might not be unique, but there's some combination that gets us a MaxVal. That combination has to include at least one of item 0, item 1, item 2, or item 3. If it doesn't include any of those items, we're saying the best you can do is put nothing in your bag. And that's kind of a pathological edge case. So there's 4 cases. So let me start with case 0. Case 0 says the best solution includes item 0. Maybe just one of item 0, maybe more, but it includes at least one of item 0. Case 1, best solution includes item 1, and so on. And these may overlap, don't worry about that. The only argument at this point is that whatever the best solution is, it's got to include at least one of items 0, 1, 2, or 3. Does that make sense? Okay, let's just look at case 0. Suppose our best possible value for MaxVal, our best value that we can get, includes putting at least one of item 0 into our bag. Well, let's do that. Let's take one copy of item 0 and put it into our bag. And right now, that's the only thing in our bag. So our bag's completely empty except it's got one copy of item 0. Okay, there's 2 things that have happened. One, whatever the value of item 0 is, we've got that much value in our bag already. Agreed? 2, we've diminished the capacity of our bag by however much item 0 weighs. If our capacity was 10 and item 0 weighs a pound, now our capacity is only 9. If our capacity was 20 and item 0 weighs 5 pounds, now our capacity is 15. So whatever our original capacity was, it's been diminished by the weight of item 0. Okay, so what have we done? We took item 0, one of them, we put it in our bag. We've got some value from that, and now our capacity is lower. So you turn to a friend and you say, hey, can you solve a knapsack problem for me? I have a bag that can hold this much. Tell me what the maximum value is I can get out of that. and they say, oh, 15-pound bag, yeah, the best you can do is $107. Okay, $107 plus the weight of item 0, that's the most value that I can get from my 20-pound bag if I put item 0 in it. So if I take the value of item 0 and I add MaxVal of this diminished capacity, I can call that C0. That's the best I'll get if I put item 0 in my bag. If I put item 1 in my bag, same thing. The value of item 1 plus the maximum value I can get from a bag whose capacity has been diminished by the weight of item 1. And same thing for C2 and C3. Since I know I have to put at least one of items 0, 1, 2, or 3 in my bag, and in each case, the best value I can get out of my original bag is either C0, C1, C2, or C3, my value for MaxVal cap is one of these things. It's either C0, 1, 2, or 3. How do I figure out which one it is?
You can compare each case.
And what am I looking for?
Which one's the greatest value?
Which one's the greatest value? Whichever one of these is the biggest, that's the maximum value I can get out of my original bag. So just return the largest of C0, C1, C2, or C3. That's our whole MaxVal function. And that's the guts of PA5. Now there's one or two details I've fluffed over. One is, suppose we have a bag whose capacity is 1 pound and item 0 weighs 10 pounds. This is not a valid calculation. Because I'm saying, okay, if I put this 10-pound item into my 1-pound bag, I get the value of that item plus whatever I can put in a bag whose capacity is negative 9 pounds. That's physically not meaningful. And even if MaxVal returns 0, that's still not a valid answer. Because I'm supposing I can put this 10-pound item in my 1-pound bag. So when we're calculating these, we don't want to do this calculation if this number is negative. So we only do this for items that'll fit in your bag, basically. So this is really just a big for loop that goes through each item and calculates a possible solution, but it only does this calculation if the item fits in the bag. And how do you find the largest of these? Well, initialize your largest to 0. And each time you calculate a possible solution, if that's bigger than your largest, set your largest equal to that solution. When you're done with your loop, your largest will be the largest. So just like the way you find the largest if a user's typing in a bunch of numbers, you don't save the numbers and then call some largest function. You take each number, compare it to your running largest, and update it if it's bigger. The other detail, and this isn't really an edge case, but if the capacity is 0, return 0. And if you code up your largest piece correctly, that'll happen automatically, but as kind of a way out of the recursion, if you're asked to find the max value from a bag that can't hold anything, the answer is 0. Yeah?
Well, isn't this technically taking all the items of the bag and comparing it one at a time?
It's actually not. So, I'll give you your $2 later for leading into the next question. So, let's look at what this is doing. So, let's suppose we want to find the maximum value of a bag that holds 10 pounds. And let's stick with this inventory. Well, there's 4 possibilities. We could put in item 1, which gets us $10, plus whatever the maximum value is we get from a bag that holds 9 pounds. We could put in item 2, which is $21, and then we have 8 pounds left over, and whatever we can get from that. We could put in item 3, which is $56, and then find the max value that goes in the remaining 5 pounds. Or we could put in item 4, which is $78 plus max val of 3. Okay, so max val of 9 is going to be 10 plus max val of 8, or it's going to be 21 plus max val of 7, or it's going to be 56 plus max val of 4, or it's going to be 78 plus max val of 2. And we can do the same thing under here and the same thing under here. And let's just drill down into max val 3 because that'll end quickly. So max val 3 is either $10 plus max val 2 or $21 plus max val 1. Max val 2 is 10 plus max val 1 or 21 plus max val 0. And max val 1 is 10 plus max val 0. And max val 0, we're not going to recurse, we're just going to return a 0. But there's tons of things that come out over here. Right, and this is just for 4 items in your inventory. If you had 50 items in your inventory, you'd basically have 50 branches on each of these. And every time you branch, you have another 50 times, right? So if you go down n levels, it's 50 to the n, so this is like 50 to the 50th possibilities. But here's the thing, with dynamic programming, we're going to prune most of this tree. The first time that we calculate max val of 8, we're going to save its value in an array. And over here, we're not going to do any of those calculations. And so it's going to turn out we have to calculate max val of each thing exactly once. And the largest max val we have is 10. So this is really just going to be a handful of calculations. And this is a great example where dynamic programming just slashes the computation time. And you can hobble that, you can take out the little tweak to your code that does the dynamic programming and run this and see how badly it performs. And then by just saving these values in arrays, it'll speed up nicely. All right, so this is the essence of the algorithm, and probably in your group what you want to do is spend some time working through this with some examples, talking about it, thinking about it, because you really want to understand this perfectly before you write any code. If you start trying to write this code and write your largest function without understanding what this is doing, you're going to go down a hole. And when this starts to make sense, you're going to be so far down another path, I'm mixing my metaphors, that you're going to end up with a situation where I know what I want to do, but my code is just kind of like this big long thing that's doing all this stuff and I can't get it to work. Case 0, case 1, case 2, case 3. All right, so let's look at the assignment itself. So we're working in groups up to 4 people. Make sure that your code has a comment block in the beginning with the name of everybody in your group. Full names, first and last name, please, so I can link them to Canvas. If your name's not in there, you don't get credit for it. I'd like 1 submission per group to Canvas. If there's multiple submissions, I'll end up grading whatever the first one is. So make sure you coordinate this among your group members, who's going to turn this thing in. And then, like I say, in task 2, you want to think about how you're doing this. Keep some notes on the group aspect of it and be ready to talk about that during the presentation the last week. So call your program PA5, please. PA5 takes a single argument, which is the capacity. So there's sample code on the server. So I have a knapsack.data file under /temp, so you can copy that into your home directory. And it's just 3 columns. So the first column is the weight of the item, the second column is the value, the third column is the name. And then V3 is the name of the sample, sorry, PA5 sample is the sample program. And when you run it, you have to tell it how big your capacity is. So if my bag can hold 100 pounds, it'll tell me, here's the inventory of items, capacity is 100, the maximum possible value is 1120, and the way to do that is to take 20 books. And if I do 99, then it takes 17 books and 2 cars. So you can run this code on the server and compare it to what you're doing to sort of double check answers. Alright, so your program is called PA5. It takes an argument, which is the capacity. It reads this knapsack.data file, which is in the directory you're running from, and it's just a set of triples. I'll come back to this big paragraph in a minute, and the boldface thing. So you want to use dynamic programming. So this is one case where I'll let you use a global, which is to make a global array of save values, because we want every version of MaxVal to use the same array. That's the whole point of dynamic programming. So you can have an array of saved values, and before you do all of this recursion, all of these calls to MaxVal, first thing you do in MaxVal, see if you've already calculated that value. If you have, just return it. Alright, and also print out a copy of what's in knapsack.data in the very beginning. So, like I said, you have sample code. So when I run this, it shows me a copy of my inventory, and then the bag's capacity, and then the highest possible value. I'd like you to do error checking. So if you run it without an argument, tell the person they should put in a capacity. If they don't put in an integer, tell them they should put in a capacity. If they put in an illegal number, right, remind them what the range of numbers is, and so on and so forth. So simplifying assumptions, right? I always put these in here because you could spend your lifetime writing this program dealing with special cases. I'm trying to make sure that you can spend your time and energy on the parts that I'm most interested in having you work on. So we can assume a maximum of 128 items in the knapsack file, which means that these arrays that you're going to store things in can just be, you know, integer weight bracket 128, integer value bracket 128. Integer or car star name bracket 128, or make a structure that holds, you know, a weight, a value, and a name, and make an array of 128 of those. Yeah?
Did it say that 0 was an invalid capacity?
0 is an invalid capacity. It's got to be between 1 and 1024. So yeah, this is another simplifying assumption. The most you can have in a bag is 1024 pounds, which means that your save array only has to hold up through 1024. So make it probably a 1025 array, so you can store 0 through 1024. So no mallocs anywhere in this. Okay, you don't have to do any dynamic allocation. And each item name in the backpack is limited to 32 characters. So you can use car bracket 33, 32 characters in a null terminator. No need for a dynamic allocation of memory. And I'm assuming the name doesn't contain any spaces. So a new car, right, I put underscores in there. So you can scan that with a %s. %s only scans up to white space, but since there's no spaces in the name, you can scan with %d, %d, %s, and that'll work fine. Part of what you should do, though, if the knapsack data is invalid or if it can't find knapsack.data, print an error message. And for those errors, you know, just exit the program after telling the user. Okay, so this is the gist of what the program does, and this is what we've been talking about for a few minutes. Compute the maximum value for a capacity of X And the way you do that, if x is 0, return 0. Otherwise, return the maximum of all of these things. So the value of item 0 plus the max val when you diminish the capacity by the weight of item 0. The value of item 1 when you diminish the capacity by item 1's weight, and so on. Find the largest of all of those, return that. And that highlighted section is really the guts of PA5. Okay, that's the part of the algorithm that you really want to make peace with before you start coding. And when you believe that, right, then the code that we have over here might make some more sense. Right, but you won't even need this, because if you really grok that, then you can write code to find that maximum. Really, really important detail though, if x minus w1 is negative, don't consider this term when you're looking for the maximum. Okay, don't just treat that max val as a 0, you'll get wrong values. So throw some if statements in your loop and don't calculate this unless x minus w1 is non-negative.
Yeah, so then I don't think that you can just get an infinite amount of things out of it.
Yeah. Or one of this really valuable item, even though it weighs more than your bag can hold. All right, so one more feature, I was going to say complication, one more feature. I also want to see how many of each item gets you that maximum value. Now, the most important part is when you run this, tell me what the maximum value is. But I also would like you to try to get it to show me how you get that value. But I would leave this for later. It'll take some rewriting to put this in, but really get the other part working first. And once you understand this, then actually getting the inventory that gets you that max value is pretty straightforward. And I'll tell you how to do it right now, but it may not make a lot of sense yet. But basically, this calculation right here is showing me the best solution if I include item 0. Okay, this calculation is showing me the best solution if I include item 1. Suppose that when I do all of this comparison, it turns out this is the biggest value that I got. Okay, this was bigger than C0, C2, C3. So it tells me the most I can get out of my bag comes from putting in one of item 1, followed by whatever gets me this max value. Now, if I set up max val so that in addition to returning the actual value, it also returns the count of how much of each item I should have, all I got to do is bump up the count of item 1 by 1. And that's the inventory that gets me the max value for this capacity. Because that's what this equation is saying. It's saying take the max value from here, so find out how many of each item get you that max value. And now increment the count for item 1, because I'm also adding in one more of those. So it's a very simple calculation, but to be able to do that, you somehow need to have MaxVal return the list of how much of each item you should have. And you can't make that global. That's absolutely got to be local to each instance of MaxVal. So you need to pass back some kind of structure that stores an inventory and a value or something like that, and then take it apart. So like I say, if you do this, you'll need to do a little bit of rewriting, okay? But this is not a bad thing, because you write your code and you spend 2 weeks on it and you turn it into your boss and they're like, this is fantastic, this is exactly what I wanted, except can you also do blah, blah, blah? And it like totally changes your program, right? I can't tell you how many times this happens. But if you understand your code and if it's well commented and if it's modularized and so on and so forth, there's a chance that that's not going to be a major headache to go ahead and make those changes. And that's what this kind of change is. It's like, okay, I need to return something more than an int, so I'm going to change that to return a structure. Well, if you write your code in a way that's sort of well organized to you, then that's not too bad to do. And then you can go ahead and you can add this update of the inventory. But like I say, sort of leave that towards the end, but be aware that that does come up later on. All right, I think that's all there is to say for now about PA5. So think about that. We'll talk more about it on Monday, and then we'll look at some other applications of dynamic programming besides knapsack problems.